So, welcome back to this course. So, in the last lecture we saw that the different properties of nuclei, how we determine whether a nucleus has a spin 0 or not equal to 0, and what are the different combination of atomic weight and atomic mass which helps in determining. And I also showed you this periodic table where you can see that many of the nuclei can be studied by NMR either in their natural form or their isotope. So, today we will continue with that and look at what are the most common nuclei and how NMR spectroscopy is actually carried out. So, if you look at this slide, the most common nuclei that we study is listed here. So, typically of course 90% of the NMR is carried out on protons, and the next most popular nuclei is carbon 13 nucleus, and third is phosphorus 31. N15 is also very popular nucleus, especially when we are looking at biomolecules. Fluorine 19 is also very popular, especially in the drug industry, in the pharmaceutical drugs. Many of the drugs have fluorine, and fluorine is also very close to proton in terms of sensitivity, and which we will see. And silicon is also useful for materials. So, these are basically the most popular nuclei, and the interesting thing is all of them have spin I equal to half. So, you can, for spins which are half integers, that is I equal to half, they are very easy to study, and the basic phenomena can be easily understood and explained. So, we will focus the rest of the course on these particular nuclei, and so let us see how NMR spectroscopy works. So, the main thing in NMR, as the word stands, nuclear magnetic resonance. So, we have to go, let us go step by step and look at what is. So, we have looked at the first part of this terminology, nucleus. So, we saw that nucleus is what is important, the spin of the nuclei. So, the next thing is magnetism. So, let us look at magnetic field. So, if you take a sample, so this is a schematic drawing here of a spin which is shown in this form. So, as I said, spin is actually an abstract quantity, but we still associate with it the properties of a motion, that is spin. So, this is a spinning nucleus, and now imagine that you have a lot of spins in the sample. So, let us imagine for example a glass of water. Water has a lot of molecules of H2O, and each H2O has hydrogens which are the nucleus which we are going to look at. So, these many nuclei together in a sample are oriented randomly in absence of a magnetic field, that is in a natural situation, in standard conditions. However, if you apply a magnetic field, this nucleus, now what happens is they are having a spin and they have a charge. So, remember the total nuclear charge is positive because of protons. So, it is the total nucleus is charged positively, and at the same time it has a spin associated with it. So, this combination of charge and spin renders it as a magnetic property. So, it becomes, now it has a magnetic dipole associated with every nucleus. So, every nucleus which has a charge and spin is now a magnet, a small magnet. So, we can associate with the magnet what is called magnetic dipole, like similar to the magnets which you see in day to day life, we call it north pole and south pole. So, we associate a dipole moment and magnetic dipole moment with every nucleus. So, you can see that if you take a collection of spins, they are basically a set of magnets in the sample. So, now these tiny magnets are very tiny because nucleus is very small. These tiny magnets, when they are put in a magnetic field, now they will start what is called as aligning with the magnetic field. So, there is some of the spins will be parallelly aligned with the magnetic field, where the north pole is facing the south and the south pole is north, facing the north pole, and anti-parallel means opposite aligned spins. And why is this happening? This happening because there is an energy of there is an interaction of these spins with the magnetic field, and this is what we will be looking at throughout this course, is the interaction of this nuclei, that is nucleus which is a magnet with the magnetic field, which is the central, which is the most important idea or the concept in nuclear magnetic resonance. So, if you look at now a nucleus now which has now a magnetic dipole moment, just now which I mentioned because of its charge and spin, and that magnetic dipole moment is denoted like this. It is equal to gamma into I. Gamma is basically a constant for a particular type of nucleus. It is known as gyromagnetic ratio, a very important this one, a ratio which is very important parameter which is used in useful for understanding NMR. So, we will So, this is the gamma, and the next value, next term here is called nuclear the spin angular momentum, that is called I, angular momentum is I. So, now this mu is a vector quantity because it has a direction, and similarly I is a vector quantity because it has a direction. So, therefore, I can now split this mu into 3 components, that is Ix, Iy and Iz, and we will look at that now. So, this mu, that is the magnetic dipole, which is shown here schematically, this interacts with the magnetic field. So, when we apply a magnetic field, this magnetic dipole moment interacts with the external magnetic field, and this energy, this interaction is given like this by this formula, where E is equal to minus mu dot, this is a dot product with the magnetic field. So, as I said, we can now split this into 3 components, mu x, mu y, mu z, and this can be bx, by, bz, but assuming that I apply a magnetic field in the z direction, what happens is the x and y components are gone, and therefore, only the z component of mu remains, and therefore, this is simplified and it becomes minus mu z bz. Okay. Now, minus mu z is basically, now if you look at this term here, it is mu z is nothing but gamma into Iz. So, that is what is written here, it is gamma into Iz into B0. So, this B0 is called as a magnetic field. So, this is our external magnetic field which we have applied, and typically we say that it is applied along z direction, and therefore, the total final energy of interaction becomes equal to minus gamma Iz B0. So, this is the one of the important concept. Now, according to quantum mechanics, that if you have a spin I, it has a possibility of 2 I plus 1 spin states. Now, what is a spin state? Spin state is basically what I was referring to as energy levels in the previous class. We looked at different energy levels. We showed that there is what is called a ground state and an excited state. Similarly, the energy levels, this the angular momentum, which is denoted like by I, is also we say is quantized, and it has different levels, and that is there are 2 I plus 1 levels. For example, suppose I is equal to half, which is the case for protons or hydrogen, and then if you multiply 2 into half plus 1, it becomes 2. So, that means a hydrogen atom or hydrogen nucleus has now, which is a proton, has now 2 spin states, that is 2 spin states, and that is given by either the plus half or the minus half. So, this is what we will put here, that means this Iz has 2 possible values. The Iz can either be plus half or minus half for a spin which is total spin is when I equal to half. So, this is basically now if you look at this formula again, if I put the value Iz equal to half, it becomes minus gamma half h cross into B0, where h cross is what is shown here, and if it is plus minus half, it becomes minus gamma into minus half into B0 h cross, that becomes plus. So, in other words, we can see that now this energy of interaction has 2 values depending on whether your the spin Iz is either plus half or minus half. So, by minus half it becomes positive if you refer to the previous formula, and if you look at minus half plus half, that is it becomes minus value. So, therefore, what has happened that we have now created 2 energy levels because of this interaction of the nucleus with the magnetic field. We have ended up with now 2 spin states or 2 energy levels. One energy level corresponds to the lower energy value, which is when the spin is in plus half state, that is plus half, that is called alpha state, and when Iz is minus half, the total energy is positive as shown here, and that is the upper, that is the excited state, and that is called as beta state. So, what has happened now, basically when we apply energy magnetic field which we call as B0 and put a sample in that magnetic field, all the nuclei in the sample now are exposed, now are split into 2 energy levels. Now, that energy, one ground state energy level and an excited state energy level, and the ground state energy level is called as alpha and the excited state is called beta. So, this is what we talked about now in the nuclear magnetic resonance terminology. We have looked at nucleus, we have looked at magnet. Now, the next term is resonance. So, what happens next? So, what happens next is essentially you supply an energy which will take the molecules from the ground state and take them to the excited state. So, this energy has to be exactly equal to the gap between the two energy levels, then only the molecules will absorb, and this is the basic idea of spectroscopy which we looked at in the previous class. So, what happens is, if I apply an energy which matches this energy level gap, this is called resonance. In resonance, basically the molecules which are now in alpha, the ground level alpha state, they get excited and they absorb the energy and they go to the beta state. So, this is basically the idea of resonance, the concept of resonance which comes in the terminology of nuclear magnetic resonance. So, you see we have completed this three terms, nuclear magnetic resonance. So, basic idea of NMR is now can be said as follows. You take a sample which has containing molecules in which the atoms have non-zero, the nucleus has non-zero spin. Take the sample in a magnetic field, the magnetic field let us say is applied along z direction. The molecules now get distributed into two populations, two states alpha and beta because of their interaction with the magnetic field, and now you take the molecules which are in the ground state and excite them to energy by applying an energy which is equal to the difference in the energy level, that is delta E, and that take them to the excited state, and that is called resonance. So, this is basically the whole idea of nuclear magnetic resonance, hence the name which NMR comes from. Okay. And the strength of the signal which is absorbed is now proportional to the difference. So, what happens in NMR is that you have a lot of molecules in the ground state and you have some molecules also in the excited state. So, when we shine a radiation which is equal to delta E, the molecules will go from here to the excited state, at the same time the molecules will come from beta to ground state. This is called stimulated excitation and stimulated emission. So, therefore, the total net how much energy is absorbed will depend on the difference in the population of how many molecules are here minus how many molecules are here. If they are equal, then there is no net excitation and the signal will be 0. That means, no NMR radiation will be energy will be absorbed. But if the difference is not 0, suppose you have more in the alpha state and less in the beta, there will be more signals, more molecules absorbing than more molecules coming down. So, therefore, there is a net positive absorption of the energy, and that is what we do rely on NMR. That means, it all depends on the net difference. The word difference is very important here, the net difference in the population between the two states. So, this population difference is a very important term, and this is applicable in general across all spectroscopy. Wherever we talk about energy quantization, we talk about population, because molecules are not always exactly equal to here and here, there will be always a difference, and that difference comes from a very famous law known as the Boltzmann law. So, we will look at this Boltzmann law now. So, what Boltzmann law says is that there is always a more energy, more population in the ground state, that is when its spin is minus half, that is alpha state, compared to the upper state. That means, in the in the equilibrium scenario, standard conditions, you will always have more molecules which are sitting in the ground state than in the excited state, and this ratio of the population is given by this formula n by n half by n minus half equal to this e raised to minus delta E over kT. So, this is a very famous Boltzmann law, we universally obeyed in nature. So, where K is a Boltzmann constant and T equal to the temperature. So, let us look slightly go deeper into this concept now. So, what it means is, suppose I take a given value of B0. So, typically in NMR, as you will see in the coming slides, we have what is called a Tesla. So, B0 the unit of magnetic field is Tesla, and based on these values, if you put in these values which we will see in more detail later, but for now if you put in these values which is typically used in NMR, it turns out that the ratio is just slightly above 1. So, what it means is that the alpha and beta states are almost equally populated, though not exactly equal, they are almost equally. So, the difference between the ground state and the excited state is very small. Now, if the difference is small, remember according to the previous slide, the absorption of energy is also small. So, the difference if it is more, the absorption is more. So, in other words, what we are looking at is the sensitivity. What is the total amount of radiation or light absorbed by these molecules, all depends on this difference, and in NMR the difference is very small, and that is one of the reason we say that NMR spectroscopy is very weak, low sensitive technique compared to UV, IR or other spectroscopy techniques. The reason being that the difference in population between the ground and the excited state is less in NMR compared to other techniques. So, now let us go further into this Boltzmann population difference. So, as I said, the sensitivity means we will look at sensitivity in again in later on, but sensitivity, as I said, is depends on how many molecules absorb the energy, and that depends on the difference in the population. So, if I want to increase sensitivity, I should increase the population difference. That means, I should have more molecules sitting on the ground state than in the excited state. So, this difference is what matters. So, that if you see here in this picture, you have almost all the spins are equally populated, I mean the two states are equally populated, a small difference is there. However, if you see in this picture, we have increased the difference in the population. So, I have more molecules sitting in the ground state than excited state. So, this is what is always strived people strive about in NMR. How do we increase this difference? Because finally, this is what matters when we record a spectroscopy spectrum, is how much is the difference, and the difference come from various factors. And as I said, one of the thing, if you go back to the Boltzmann law, the difference comes from this factor here. So, if I increase the B0, this B0 value, that is a magnetic field, I can increase the difference, because if you look at this mathematical formula, if I increase delta E, e raised to minus delta E will go down, which means that the less number of nuclei will be here and compared to n alpha. So, what we are trying to do here, we are trying to increase this n alpha compared to n beta. So, relative ratio, and that is governed by this famous Boltzmann formula equation. So, here you can see I can either increase gamma, this is a constant, h I cannot vary, I can change the B0, make it very high value, I mean increase the value, or I can decrease the temperature, right. And so, this k is constant. So, h and k is constant. So, if I decrease the temperature also, I can get this difference. So, these are the three basic parameters which basically determine the sense. So, this is what is shown here, that if I want to increase the difference in population, that means I want to increase the sensitivity, I have to basically rely on three parameters. Either I go to higher gamma value, or I can increase the magnetic field, or I can lower the temperature. Okay. So, based on these different parameters, the population ratios will keep changing, and essentially what NMR spectroscopists strive is to go by the best possible parameters, optimal parameters in this. So, for example, gamma, highest gamma in the whole of NMR is proton, and the whole of the periodic table which I showed you, highest is gamma. So, obviously, gamma is the most sensitive nucleus or atom which can be studied in NMR. Magnetic field is something which is in our control, we can increase the magnetic field. So, if you go to higher and higher magnetic field, you can actually increase the sensitivity, and we will see later this how important this is, and it also contributes to the resolution of the spectrum. And of course, lowering the temperature is another parameter which is also under our control. So, we can lower the temperature, but again in solution you can't do much, because in solution the lowest you can go is 0 degrees, because below that the sample will freeze depending on the boiling freezing point of the solvent. But typically when you take a water sample, you can't do much, because the lower, below 0 degree the sample freezes. So, therefore, temperature, although is a very important parameter, is not so much of importance as much as the magnetic field and gamma is considered. So, therefore, this is how we increase the sensitivity of NMR spectroscopy. Now, the whole this is what is called quantum mechanical picture. So, we are looking from quantum mechanics point of view. You can also look at NMR from a classical point of view. So, there are two different ways to understand NMR. So, this is again one of the unique technique, spectroscopic technique, which can be understood both from classical pitch perspective as well as quantum mechanics. Typically, all spectroscopic techniques are understood from quantum mechanics point of view, but here we will also show how we can actually understand from a classical picture. So, in a classical model, you can visualize like this. You imagine that there is a nucleus which is now spinning around its axis. So, this is a nucleus shown. Now, there are two possibilities, it is having alpha state and a beta state, which is shown here. Now, what happens is when you apply a magnetic field which is shown here B0, the spins now start to precess, means move around, revolve around this magnetic field. This is called a famous Larmor precession. This is derived, can be derived and is derived in many of the test books, which we will not be able to go in detail the derivation, but the idea is that the spin now start moving around the magnetic field. Is like a something similar to the earth going around the sun. So, this is what is called precession, and this precessional frequency is actually given by omega equal to gamma B0. So, this is the derivation which can be found in many books. So, this is what is the central idea, is that the precessional frequency of the spin around an external magnetic field is given by gamma B0. Now, if you look at the quantum mechanical picture, this is what we have been looking at in the last few slides. There we talked about the energy levels, and here also if you see the difference in energy level, the delta E is given by this, the energy of difference is given by omega, the frequency, this is the frequency at which the molecules absorb the radiation from ground state to excited state, and that difference delta E is equal to h mu, and that is related, the frequency of excitation is now given by this omega 0 equal to gamma B 0. So, you see there is an exact match between the two, which is expected because we are looking at the same system from two different perspective, but what is interesting is that whatever you understand, whatever we can see from NMR quantum mechanics point of view can also be understood from a classical point of view. So, many of the times you will see that we will be using this classical picture model, this picture what you are seeing here on the screen. This is what we will be using to explain many of the NMR phenomena, but remember the main thing is also what is can be explained based on this picture. So, we will be essentially going back and forth between these two pictures just in case whenever depending on the requirement. So, now let us look at the classical picture in little more detail. So, this is what I was showed in the previous slide, that the frequency of precession, the frequency at which the magnetic the nucleus precesses around magnetic field is given by this frequency omega mu equal to omega gamma B0 by 2 pi. Now, here the B0, so that is what the units of B0 as I said is measured in units of Tesla, or it can be in units of Gauss. So, if you see the mu is a frequency unit, right, it is a megahertz, it is in hertz, whereas B0 is in the Tesla. So, if you multiply this gamma, which is you can see from a table, a lookup table, if you multiply you will get this value of mu in the typical range of megahertz, and that is why if you see all the NMR systems wherever we have is typically we talk about in megahertz. So, we say that we have a 300 megahertz spectrometer, we say we have a 500 megahertz spectrometer. So, these numbers megahertz and these numbers 300, 500, they are all coming from this Tesla. So, essentially the magnetic field is what is determining the frequency. So, when somebody says that I have a 500 megahertz NMR spectrometer in my laboratory, what he means to say is that he has a magnet which is 11.75 Tesla. So, the point here is that the spectroscopy, the frequency depends on the magnetic field directly given by this formula. And to just put it in perspective, the Earth's magnetic field is very small, it is 0.5 Gauss, whereas if you look at this, we are talking about in the 10 to the power 4 Gauss in the typical laboratory magnetic field. So, the magnetic field we use in NMR is really orders of magnitude very high, higher compared to what is Earth's magnetic field. So, therefore, we are using very strong magnetic field, and there are associated precautions which has to be taken practically that we will look at when we come to the hardware aspect. So, now coming to this classical picture, just as I said, we will be toggling between these two different pictures, and it is sometimes very easy to understand NMR from a classical point of view and sometimes from a quantum mechanics point of view. So, let us now look at this classical picture model. So, what this says is that imagine one nucleus which is like this, which is having a spin, like again the same analogy, the analogy you can use is the earth is spinning around its axis and also it is revolving around the sun. So, we can use that picture keep that picture in mind. So, there is a nucleus which is now precessing around the magnetic field. Now, this is about one nucleus, one hydrogen atom, but remember in a sample we will never have one hydrogen atom. What you will be having is a collection or a number of hydrogen atoms. For example, let us take a water sample, you take a glass of water, the concentration of water is 55 molar, which means there are 55 moles of water in 1 liter, and 1 mole is 6 into 10 to the power 23. So, therefore, you can see there are so many different 10 to the power 23 atoms of hydrogen. So, therefore, if you look at all those hydrogen atoms together, you will get a picture something like this, which is shown on the right. So, here you see each nucleus I am showing as an arrow, is shown as an arrow here. So, each nucleus is an arrow. So, you can, this is although there are only a few arrows shown here, in reality imagine that you have 10 to the power 23 or 10 to the power 20 atoms with nucleus which are all like this. So, and therefore, you have now some of them pointing upwards, those are the nucleus which are in the alpha state, and remember there are also some in the ground excited state, that is beta state, and they are lesser in number because of the Boltzmann principle which we saw, and that is pointing downwards. So, now if you look at each of these vector arrows, what is happening here is that now this vector arrow, if you look at in this frame. So, let us now draw a picture of how this looks like. Let us see, this is the z axis, which is what is shown here, then you have an x axis and you have a vector something like this. Now, this vector can be now have two components, it will have a z component and x component. At the same time, there is also a y axis, so it will have a y component. Okay. So, this is a y component. Now, if you look at another vector which is in this direction, for example, one of the other vector here, now that will have a component along again minus x, and it will have along z this component, and it will also have along y axis. So, if you see this component, this which is minus x component is exactly cancelled by what is here. So, this will cancel each other and there is no vector, no net component in the x axis. So, we can say that x component is equal to 0. Similarly, if you look at y component of some other pair of nuclei, some pointing here, some pointing here, again in the y axis they each other and y component also becomes equal to 0. But if you look at the z component, what is along the z axis, this is this component which is drawn here, this is always pointing in this direction, no matter what is you take, it is always pointing in the z axis. Therefore, the z component is never equal to 0, only the x and y cancel each other. So, if you look at, so this is the picture we have to keep in mind, that whenever you have a net this one, you will basically end up with a net z component and all the x and y becomes equal to 0. So, this is a basic idea in a classical picture, that all the x and y component cancel out, you are left only with the z component, and that is what matters. Now, if you look at this phenomenon where x and y goes to 0 is because all these arrows which is shown here, they are pointing all in the random directions, they are not together, they are fanned out like a cone. So, this is like a cone and all of them are fanned out, means distributed all along this cone, and therefore, this thing becomes 0. This would not have happened if they had not been along in random direction. So, therefore, we use the word random phase approximation. So, random phase approximation is a term used in NMR to denote that the spins are all randomly located in a cone and they are not aligned with each other. So, this is called random phase approximation, and now what, because of that only the z component adds up, but all the x and y cancel. This is as far as alpha spins are concerned. Now, if you look at the beta spin, the same scenario will happen. In the beta spin, same thing, the z axis will add up in the minus z, but x and y will all cancel each other. So, therefore, you will end up with minus z value and here you end up with plus z value. So, now the plus z value whatever is here will start subtracting from the minus z value which is here. So, therefore, you end up with finally what is known as a net spin vector. So, we will look at the final picture which emerges because of this consideration. What is happening now, if you see here in the generally, so that means that the positive z values will actually cancel with the negative z values, and that will result in a net vector which is now pointing in this z axis. So, this is our final magnetization. This has come because the positive z values which came up from here from the alpha spins cancelled with whatever was in the beta, but these are not equal, because remember according to the Boltzmann law there is more population, more molecules in this side compared to more molecules in that side, and therefore, there will not be always exact cancellation of the z value, and the z value will be positive because more spins are up on the upside than downside, and this vector what you see here is called the net magnetization. This is the popular word which we will use in NMR, and this is a positive direction z axis, this is where we apply the magnetic field. So, whatever NMR is done is now carried out with this particular magnetization. So, all NMR spectroscopy techniques what we will see is all based on looking at this net. So, before we look at this, what the thing you should keep in mind is, suppose that alpha molecules, the number of molecules alpha state are let us say equal to molecules in the beta state, then what will happen? What will happen is these two z values will cancel exactly and it will become 0. So, when the magnetic vector this is 0, it means alpha state and beta state are equally populated, but when alpha state is more populated than beta, then this will be positive. If beta state is more populated than alpha, then this will become negative. So, therefore, this magnetization vector all depends on what is the population between in the alpha state and the beta state, and that is what is the whole idea of NMR. You manipulate the population by applying some radio frequency energy, and based on that manipulation the molecules the magnetization vector will either be positive, 0 or negative, or it can come in any other direction. So, we will see now in the next class how this magnetic vector is manipulated and how NMR data is recorded.